Let's take a look at our ionic compounds and this concept called lattice energy. So in an ionic bond, everything's held together by that electrostatic interaction. This is governed by something called Coulomb's law, which looks at the distance that things are apart from each other and the charges each thing has. When we have a large nuclear charge, we have stronger attraction, we have more energy. When we have a large distance, okay, the d is the distance between the nuclei, then we're going to not feel the charge as much and the energy is going to be less. Okay, so more charge, stronger attraction, more energy, more distance, less charge is felt, less attraction, smaller energy. Okay, and then this is just a diagram of Coulomb's law showing, the distance between them affects that interaction. And then if you've got something positive and negative, they're attracted. If you have two things that are negative, they're going to repel each other. Okay, so when I look at lattice energy, okay, we are looking at this formation of a compound from the gaseous ions. We get a delta H value. We get some enthalpy going on there. So we're going to look at lattice energy. We're going to look at the enthalpy of formation, all sorts of stuff. But lattice energy, the energy associated with the formation of a crystalline lattice of alternating cations and anions from the gaseous ions. Okay, and so that's what our lattice energy is. All right, now when I look at lattice energies, I can look at a whole bunch of different things. So if I'm, going to consider something like lithium fluoride, I would find my lithium cation, my fluoride anion, and there would be my lattice energy. Okay? All right, so now when I look at lattice energy, there's a few things to consider. All right, lattice energy is going to depend on atomic sizes. So remember, the bigger the distance, the less that charge is felt. And so if you look here, as I get to bigger cations, okay, so I'm keeping chloride consistent, so we're keeping that chloride constant, and if I'm increasing the size of the cation, well, the distance between the nuclei is going to increase, and so the lattice energy is going to go down. So as we go down the periodic table, the radius of things goes up. All right, the potential energy of oppositely charged ions becomes less negative the further they are from each other. Okay, and so as the radii increase down the columns, the ions can't get as close to each other, so the energy released when the lattice is formed is less because they just don't get as close to each other. There's too much distance between them. Okay, so we're going to depend on the atomic sizes. We're also going to depend on ionic charges. So here I have sodium fluoride and calcium oxide. Sodium fluoride has a lattice energy of 910 kilojoules per mole, whereas calcium oxide has 3,414 kilojoules per mole. Okay, so a couple of things going on here. They're approximately the same distance, all right, but the calcium oxide is a little further away from sodium fluoride. Now, normally the further distance would mean lower lattice energy. So here the charges are the key. So when we look at Coulomb's law, it's looking at both the distance and the product of the charges. All right. And so when I look here, my sodium fluoride, I have a +1 times a -1 for an overall -1. Okay. But when I look at the calcium oxide, I have a +2 times a -2 for an overall -4. That's a significantly higher charge there. And so the lattice energies become less exothermic, less negative with increasing ionic radius. And my lattice energies become more exothermic, i.e. more negative with increasing magnitude of ionic charges. So the lattice energy increases with a larger charge there. Okay, so now when we form our ionic compounds, some things are going to happen. First, we need to get our elements as atoms, okay? Because sometimes, like let's say we're dealing with chlorine. Well, chlorine exists naturally as a diatomic, Cl2. So I need to split that up. That's going to require energy to break that chlorine-chlorine bond. All right? Then I need to form ions. My anions, because of those electron affinities, are typically energetically favorable. And my cations, because we're ripping electrons off and forming, those cations, those are typically going to cost energy and be unfavorable. We're going to bring the ions together. This is typically favorable. And then we need to condense that solid phase, which is also typically favorable. Okay? So let's say I want to look at sodium chloride. Okay? All right. So sodium chloride, we're going to balance to 1 mole of sodium chloride. So we're going to use that weird 1/2 stuff that we did when we were looking at thermo. So I have some sodium. I need 1/2 of a chlorine. And I'm going to form, okay? So I need to do a few things here, because remember, we're doing this from gaseous things. All right, so I need to make this gaseous. Okay, so I need to vaporize. All right, and then I need to make an ion, so I need to ionize. Now I'm going to make that cation, so I need my ionization energy. Okay, to my chlorine, I need to disassociate. Okay, so I have that 1/2 because I only need 1. Okay, because my sodium chloride formula has 1 sodium and 1 chloride. And then I need to ionize this. Now I'm making an anion. So here I would need that electron affinity. Okay, so it depends on the type of ion that we are making. Are we going to use an ionization energy, or are we going to use an electron affinity? Okay, and so those two go together, the gaseous, and come up here to that. So this right here is our delta H of formation, which we've looked at those before. And on this, where I'm going from the gaseous ion plus the gaseous ion to my condensed solid, that is going to be our lattice energy. Okay. All right, and so I can look at some numbers for all of this stuff. All right, so I have some different processes here. I have process 1, process 2, process 3, process 4, process 5, and then my delta H of formation there, okay? All right, so my first process, this is where I did my vaporizing. Okay, process 2, that's where I did my ionization energy. Okay, process 3 here is my disassociation. Process 4 is where I looked at that electron affinity to make that anion. And then this was my lattice energy. Now, there's a note here. Okay, my bond of chlorine is cut in half. To 2. Only needing, okay, we only need 1 chlorine for overall. All right, my lattice energy, it costs energy to disrupt and it gains energy to form. So that's why it's negative there. All right, and then if I was calculating that delta H of formation, we're just going to look at process 1, process 2, process 3, process 4, and process 5. What does that look like? Looks like Hess's law, right? Because we just get to add it up, okay? And if we cut something in half, like the chlorine, we cut the energy in half as well. So, because remember, what is important about enthalpy? It's a state function, which is why it's path independent, okay? All right, so here I've got some numbers put in. You can see what's costing energy, what we're getting energy from. So up here, this is that ionization energy. Okay, this was a bond energy. This was the sublimation. Okay, here is my delta H of formation. This is my electron affinity. Okay, and then this over here was my lattice energy. Okay. All right. Drawing out this picture, this whole thing, this is called the Born-Haber cycle. All right, and so the sum of our steps to form sodium chloride from elemental chlorine and sodium. And then the enthalpy change of that last step is the lattice energy. Okay, and so we sum up all 5 steps to give us the delta H of formation. Now sometimes there's more than 5 steps, sometimes we'll have a process with 6 steps, because let's say we've got something that makes a +2 ion. Remember that each ionization energy is separate, so the ionization energy to pull the first electron off, and then we have the ionization energy to pull the second electron off. And so sometimes this will be a 6-step process because we'll have to ionize once and then we'll have to ionize again. Okay, again, I've got my, step 1 plus my step 2 plus my step 3 plus my step 4 plus my step 5 gives me my delta H of formation. Okay, and usually, again, that last step is the lattice energy. Okay, so notice here, delta H of the last step is delta H of the lattice energy. Okay? All right, so let's take a look at magnesium bromide. Okay? So we want to determine the energy of formation. So that is delta H sub F. Okay? So we need to know a few things. What information are we going to need to know? We'll need to vaporize the magnesium, both IEs for magnesium. We'll need to the bromine dissociation. Okay, the electron affinity for bromine, and then the lattice energy of magnesium bromide. Okay, so here I have some bond dissociation energies, I've got ionization energies, I've got electron affinities, okay, and then lattice energies. I had put on slide 12. All right. So these are all of our processes that we need to go through in order to get the information we need. So we'd need slide 12 to get our lattice energy. We're going to need to know some information about bromine. Okay, so we'll need that from here. Okay, there's my bond energy for bromine. Here's my ionization energies for magnesium. Let's see here. Here's my electron affinity for bromine. Okay, again, that lattice energy I put on slide 12. Okay. All right. So we need all this information to try to put the whole thing together. Okay, so we're going to look at getting that delta H of formation of magnesium bromide. Okay, so we're going to have a process and we're going to have some energy in kilojoules per mole. Okay. All right, so we're gonna vaporize. So we're gonna go from solid magnesium to gaseous magnesium, and that's gonna be 147.7. Okay, we're gonna need the ionization energy 1. Okay. We're going to need the ionization energy 2. All right, and so that's going to be and that's going to give us 1450.7. Okay, and then we're going to need to dissociate the bromine. Okay, we don't have to cut this in half because we need both of the bromines, so that's going to stay the 193. We need that electron affinity, so I have 2 bromines plus 2 electrons gives me... Now this one I have to double because I'm putting electrons into 2 bromines, okay? And then I need my lattice energy. And that's going to be okay. All right, so now we're going to look at our delta H of formation, and we're going to get negative 560.9. Okay, so we have to go through each of those processes in order to get our overall delta H of formation. All right, so did we do okay? We did okay. Now, when I look at something like magnesium bromide versus magnesium chloride, right? Well, magnesium bromide, magnesium chloride, we're still going to get the same charges. So here's the magnesium chloride. This is 2524, okay, for the lattice energy. And then the delta H of formation here is negative 642, whereas we just calculated the negative 561 for the magnesium bromide. So why is the magnesium chloride larger than the magnesium bromide? Well, first of all, bromine is bigger than chlorine, and so that distance is going to affect us, okay? The bromine packs into the crystal less efficiently because it is bigger. Charges can't get as close together. And then also, bromine actually gets less energy back when it attracts an electron than chlorine does. So that's going to be a difference there as well. So the energy level on bromine is further out than it is on chlorine. And so the attraction to the electron isn't as strong. And so there's a few different things going on there. It's both distance and the amount of energy that you get back when you add in that electron there. Okay. All right. Now, let's take a look at, there you go, that was interesting. I had a blank slide for no reason. All right, so now let's look at this one. I've got some sodium and iodine giving me sodium iodide. Okay, so I've summarized the information you need on this slide. I've given you some ionization energy, some electron affinities, vaporization, etc. Okay, and a lattice energy. So when we talk about calculate the energy released in the reaction, this is the energy of formation again. We're calculating a lot of delta H sub F's here. Now, I could ask you to calculate a lattice energy though, in a test or a quiz situation. So make sure that you actually understand where all the numbers are coming from and what order they go in. Common error I've seen students make if I ask for the lattice energy is they write it all out and assume they're calculating the delta H of formation because you're memorizing a particular problem instead of the process, all right? So keep in mind the lattice energy is one of the steps to get to the delta H of formation. So make sure you know what you're calculating, all right? So we're gonna calculate the delta H of formation here. So I want you to try this, pause this, the slides, try it, and then unpause to see my solution. All right, let's see how you did. Okay. So this is what we're looking at. Okay. So we're gonna have a process and we're gonna have energy. All right, so again, we're going to vaporize that sodium. Okay, and we're gonna get, okay. Process number 2, we need to ionize sodium. Okay, then we need to dissociate this is being combined into one step because the energy for this was given as a single energy, okay? All right, and then because we only need one of them, we're gonna cut that energy in half. Okay. We need the electron affinity. And that's going to be negative 300. And then lastly, we need the lattice energy. And that's negative 704. Okay, So we're going to get our delta H of formation. I'm going to take and then we put that all together, it's negative 294. Okay, so there's all your processes. Write out the reactions. Don't just write out the numbers, write out the reactions. Know what process you're doing. So again, you know, what if I asked you the lattice energy? Well, remember, okay, we're doing delta H1 plus delta H2 plus delta H3 plus delta H4 plus delta H lattice equals delta H of formation. So if you were solving for the lattice energy would be the formation minus all those other ones, right? So make sure you know what you're solving for, okay? All right, and here's one to try on your own so that you don't have to flip through all the slides and find all the stuff. I have given you the pertinent information summarized nicely on this slide, okay? So you want to write out each process. With the equation, and then calculate what is asked for, okay? Now there is a lattice energy here, so the energy released, again, you're gonna calculate the delta H of formation, okay? All right, so try it on your own, and you should get negative 91 kilojoules per mole as your delta H of formation for lithium hydride. All right, that's our lattice energy.